All right, differentiate and graph. Differentiate and graph. So this is actually not that hard to differentiate, right? The derivative of this function, right? Chain rule, okay? We would say that that x squared minus x, right? You might call that the inside function, right? So we'll call it f, okay? So that means that your derivative here is going to be f dash on f. Okay? So the derivative of this is 2x minus 1. And you've got your x squared minus x. That's it. Okay? There's no simplifying. I mean, I could factorize that, but there's not that much point at the moment. Okay? Why did we find the derivative again? What was the point? To look for stationary points, right? Okay, so I would say stationary points exist when this thing is equal to 0. Okay? Now, because it's a particularly easy function, I just want to find out when this is 0. So as usual, I disregard the denominator. Okay, and I'm looking at the numerator. Yes? When is the numerator equal to 0? It's when x is equal to a half, right? Okay, so far, so good, right? Everything seems to be going normal. And then you would start to graph it. But as you start to graph it, you come up with a problem. So let's have a look at what this thing is going to look like, how it's going to behave. Okay, this is a log function, right? Let me go back to what we were looking at before. If you just take a vanilla standard log function without any weird stuff in there, right? What's the domain of such a function? What's the domain? Or what values of x does this function exist? Well, what's it look like? This is log x, right? And you've got your asymptote here, okay? So anything greater than 0, right? I can't get to 0 itself because there's an asymptote there. So let's say the domain is x greater than 0. You happy so far? Okay. Now what that corresponds to is, if, okay, sure. If I were to give you, right, this function, right, I'm just translating. What this means is, e to the power of y should be equal to x, right? E to some power will be equal to x. And as I change what the power is, the value of x changes, right? But there's no power that I can put in here which would make e to the power of that a negative number, okay? E to the power of 0, right? What's e to the power of 0? It's just 1. As I go bigger numbers, e to the power of 2, 3, 4, 5, 100, okay? E just gets bigger and bigger and bigger, huge numbers, right? Not e, but e to the power of that. When I go in the other direction, negative, okay? E to the power of minus 10, minus 100, minus 1,000, what happens to the number? It gets really, really, really small, okay? It's because you get 1 over e to the power. Now it gets tiny, but it never goes negative, right? Okay, so, therefore, this is the domain we're expecting. But when I come over to this function, I don't have just standard old x, right? Instead of x, I've got that. So if I want to think about the domain, right, then that inside function, that has to be positive. It has to follow the same rules as I established over here, okay? So x squared minus x is greater than 0. I can factorize that. Come in. Oh, yeah. Great, thank you. So, when you think about this, what kind of graph would that be? X times x minus 1. What's it look like? It's a parabola. Okay, it looks like this. X means a root at 0. X minus 1 means a root at 1. So there's the graph. So where is the domain of my actual function? The domain of this function corresponds to when this is greater than 0. Okay, so I guess I would say the domain is x is, by the looks of things, less than 0, or it's greater than, what did we say the other root was? 1, right? Okay, so, hold on a second. This causes problems, because you look at where you found your stationary point, x equals a half, which looks like it's about there, okay? And it's not in the domain. The stationary point is not in the domain. What does that mean? Now, I'm just going to let that question simmer for a minute, okay? Because it doesn't have an obvious answer, at least I don't think. Okay? So if I don't have any stationary points that are actually in my domain, the graph that I'm going to come up with also will not have any stationary points. Okay. Now, let's come back to this, okay? Being that you've got this kind of derivative, okay, I can make some pretty good assumptions about the shape of this graph based on, okay, is it decreasing or is it increasing, all those kinds of things, okay? So what you'll find as you test some values, okay, is that, remember, I can't go past 0 on the left-hand side, okay? To the left of x equals 0, your function is, look at it, okay, when x is negative, what will the numerator be like? What value will the numerator take? It will be also negative, right? So it might be, say, x equals minus 1. So this would be minus 2 minus 1, that's minus 3. And then what do you get on the bottom? This negative will turn into a positive, right? So negative divided by positive, the gradient, that's what this thing tells you. The gradient's negative, which means it's decreasing, right? As I get closer to the origin, going from left to right, okay, what's happening to the gradient? How's the gradient changing? What's it approaching? This is the question I'm asking. What's the limit as h approaches 0 of that derivative? Now I've done the work for this already. I'd like you to go, I'm going to graph it and show you, okay, but I want you to prove it for yourself because this is how I knew what it was doing. As x approaches 0, and these values get very small, okay, the whole thing is becoming a very, very large negative number. Very, very large negative number. What would that mean for the graph? What does it say to you when your gradient is a very, very large negative number? It's really steep, and it's decreasing, right? As I approach 0. Okay, so this is the kind of shape that you get. Okay, this is the shape. I can't cross this asymptote, and then you get another asymptote. And you can, again, check out your derivative, take a limit as x approaches, I should label this, x equals 1. You get the same thing, except in reverse. It's approaching a very, very large positive number. So that's why it's increasing. It's increasing at a really steep rate. Okay. Now, what happens in here? You want to tell me? Because when you're graphing, like, say, a rational function, right? And you might get, oh, here's an asymptote, here's another one, and you've got one part, another part. You usually assume you'll have another part in here. Right? That's a reasonable assumption to make. So what's happening in this case? Any takers? Yeah?
Just randomly.
Like it could, I mean, based off this, right, it might do something up here. That would be kind of weird though as well, because this seems to be increasing, and this seems to be increasing, so maybe this should be like decreasing? What's going on? Now, the answer is, at least on this graph, nothing's going on. Because we said that the domain of this function is only to the left of there and to the right of here. Okay, so actually I'm finished, with one exception. I should probably find what these guys are. Okay, can we do that together? How would you work them out? How do you usually find x-intercepts? Y equals 0. So there's y. Okay, so I'll say log of x squared minus x is equal to 0. Now what? Say it again. Careful. Think. This is log base e, right? So when you're going back and forth. Okay, yeah. So the base of a log equation will become the base of an index equation if I rewrite it, right? So I'm going to get e to the power of 0 is equal to x squared minus x. Okay. So then this is just 1. Okay. So when you go through that, I'll save you some time. You can't factorize it nicely. You've got minus b plus or minus the square root of b squared minus 4ac, which ends up being 5. At least if I did my numbers, right? On 2A. Okay? So when you look at that, this must be the 1 plus, and this must be the 1 minus. That's it. Now, there's just one more question I have. If all you want to do is just draw the graph and get 4 marks and get home and hosed, okay? We're finished. However, I posed you a question. I wonder if you have any idea of an answer yet, which is, what's happening in here? I want to know what's going on. I said it's outside the domain, so we haven't drawn anything, right? And yet, I feel like something should be happening because the function doesn't exist there, but the derivative does. Usually, we're more used to functions that are a bit the other way around. Okay, so if you remember this guy, the cube root of x. Cube root of x. Do you remember what that looks like? Looks like that. Okay, there's a function. Or what about the absolute value of x? Now these two functions, they exist at the origin, but their derivative doesn't. Okay, like we asked the question, what's the derivative at this point? Is it 1 or is it minus 1? Answer, it's neither. The derivative doesn't exist there. But here you've got kind of the reverse thing. The function doesn't exist, but its derivative does. Now, there is a graph to this, okay? I told you it's just not going to be on this graph, because the problem is, come in.
Sorry, I'm gonna drop it again. Hand up.
Because what I need to do to actually draw these in-between parts is I'd have to come off the board, because I need a third dimension to handle this. Because actually some numbers will make this work. It just is that they're not real numbers, that's all. They're complex. You've got imaginary stuff in there which makes it work, okay? Except this is just 2D, so I've got my x and I've got my y, and I would need a z. I would need it to sort of come out of the board off at an angle, if that makes sense, okay? But my whiteboard is unfortunately limited. Okay? But anyway, so that's just to make you think. The graph does actually have a behavior in here, and this is what governs it. It's a little bit like, you know the formula for Fibonacci numbers, right? There's stuff, actually it's very convenient, it looks like that. There's stuff going on that makes the term, the nth term formula, that makes it work, it's just you can't see it. So there's stuff going on, the graph is doing something, it's just invisible to us.